Hello guys, welcome back, and in today's video we're going to describe some calorimetry experiments. Okay, so we're going to do experiments to find out what our delta H is. Alright, so we have on our hands a couple of reactions that we have learned before: combustion, displacement, when salts dissolve in water, or a neutralization reaction. So pause the video now to get the refresh on what each of the reaction is. You've already learned this before. Alright, so let's start with a combustion reaction. Okay, so in any calorimetry experiment, okay, so there is a device called a calorimeter. Okay, so it can be anything from a copper can or a polystyrene cup, which we'll see later. Okay, it is a device which is used to measure the heat flow of a chemical reaction. Now, this basic step 1 to 6 is used in all of the calorimetry experiments. Okay, alright, so I'll explain it to you step by step. So first of all, we're going to pour 100 centimeter cube of water or any amount of water into the calorimeter first, okay, by using a measuring cylinder. Alright, so in our experiment here, the calorimeter is a copper can, as you can see here. Alright, and then we're going to record our initial temperature before we do anything first with a thermometer, and then we're going to record it here, which is 21.5 degrees Celsius. Alright, and afterwards we're going to weight this spirit burner, which contains the alcohol with the lid on. Okay, so we want to weight it because after the reaction we want to see how much mass of the alcohol here has been used. Alright, so the mass of burner and ethanol before the experiment is this much. We already know this. And then afterwards we're going to light it up, okay, and then try to heat up the water and see the temperature change. Now in the process we need to stir this water mixture, okay, continuously until the thermometer reaches 40 degrees Celsius. Why do we need to actually stir this entire water throughout the experiment? Because we want our temperature to be distributed the same, okay, throughout the mixture. So our final recorded temperature is right now 62.8 degrees Celsius. And after the experiment, we weighed the spirit burner again, and we found it to be 136.58 gram. Okay, so the volume of the water that we added was 100 centimeter cube that we know. Alright. Okay, so let's do our molar enthalpy calculation. Okay, so in order to find delta H, we need to find the heat energy change divided by our mole, right? So let's find Q first. So Q is equals to mc delta T. Okay, so your mass here is the mass of this water, okay, which is 100 centimeter cube, so it's going to be 100 here. So remember that 1 centimeter cube is equals to 1 gram. Alright, C, since it is water based, it's going to be 4.2. Delta T would be the final temperature minus initial temperature, which is going to be 62.8 minus 21.5 degrees Celsius. If you put that into your equation, you will get, alright, so it will be 17346 kilojoules. Alright, so the next thing that we need to find is our mole here. So to find the mole, we need to find the mole of our ethanol which burn here. Okay, so your mole would be mass over your molar mass. Alright, and given that your mass here is going to be the mass of ethanol, right? So before the experiment and after the experiment, so this will be 137.36 minus 136.58. Alright, it's divided by your molar mass of ethanol. So ethanol formula is CH3CH2OH, which you will learn in organic chemistry later on. So the molar mass for it, if you calculate it from periodic table, it should be 46 grams per mole. So we're going to put it here. Alright, and this is grams. Now from calculating this, you would get 0.011696 mole. Okay, Okay, now that you have your mole and you have your Q, we're going to calculate your delta H. So delta H would be Q divided by mole, so it would be 17346 kilojoules. Sorry, this is simply joules. Okay, if we want it to be our kilojoules, it has to be 17.346. So 17.346 kilojoules divided by 0.01696, which would give us 1022.76 kilojoules per mole. And since our final temperature is greater than our initial temperature, this is going to be an exothermic reaction. So we need to put a negative sign here and tell them that this is an exothermic reaction. Alright, let's do another one. So the experimental value that we got from here is about 1022, right? So it should be 1022 here, but the true or the correct value should be around negative 1370. So what errors did we make, or why was the rise in temperature less than expected? It's simply because the heat that we try to supply to the water, right, instead of going directly or absorbed totally by the water, some of it is lost to the air surrounding. So heat is lost to the air rather than going into the water. And another thing is because of the incomplete combustion of alcohol, which you will learn in organic chemistry as well. It is because we do not have enough oxygen supply to completely burn this off. And how we can identify it is by looking at the color of the flame. So if it went under complete combustion, the ethanol flame should look blue. But the flame color that we have right now is yellow-orange, which means that our combustion was incomplete. And one other thing to notice in this experiment is that we might see some black, solid form at the bottom where the flame and the copper container is touching. It's because copper 2 oxide is being formed because of the incomplete combustion. Alright, so let's try a displacement reaction. So in this reaction, we'll try to use a polystyrene cup, which looks like a cup like this. So this is simply a cup that you will simply use in either coffee cups or your ice cream cups. Why do we use it? It's because it is a very good insulator of heat, and it will reduce heat loss. For example, if you put ice cream in a polystyrene cup, it won't melt easily. Same way, if you try to heat something up, heat won't be lost to the others. So we're going to place a polystyrene cup in a glass beaker, and the experiment is to find out what is the molar enthalpy change, or delta H, when zinc reacts with sulfuric acid. So zinc is more reactive than sulfuric acid. So zinc, this is a metal and acid reaction, so it will give us a salt and water. Alright, so zinc, sulfate, and water. So let's try to do a calculation here. Alright, so the volume of copper 2 sulfate was already given to us, 50 centimeter cube. The concentration is this much. We know the mass of zinc, which we are going to add, the initial temperature, and the final temperature of copper 2 sulfate. Notice that in this reaction, we need to put excess zinc inside copper 2 sulfate, so to make sure that all of the copper 2 sulfate is being reacted. Alright, so as usual, we want to find delta H, so it should be Q over mole, right? So let's find Q first. Alright, so Q is equals to MC delta T. Alright, so the mass here is the volume of your copper 2 sulfate, which is 50 multiplied with, let's say, 4.2 or 4.18. Why can we use the same as water? Because copper 2 sulfate aqueous is also water-based. Alright, so the temperature would be the final temperature minus the initial temperature, so it should be 10.3. Alright, if you use a calculator, you should get 2152.7 kilojoules, which tells us that this is 2.15 kilojoules. Now we need to find the mole, okay? So you can simply use the mass of zinc here, okay? Why? Because we're using excess zinc. And that's why we need to use the mole of copper 2 sulfate to find the mole of zinc first. So mole of copper 2 sulfate, how do we find it? We already know the volume and the concentration, so we're going to multiply it, okay? Alright, since this is mole per dm cube, this 50 should be 0.05 dm cube multiplying with 0.2 mole per dm cube. Alright, so we should get 0.01 mole. Alright, so what is the mole of zinc at this point? So 1 mole of copper 2 sulfate is equals to 1 mole of zinc. So mole of zinc would also be 0.01 mole. Alright, so it means that our delta H can be calculated now. Delta H would be Q, which is 2.15 kilojoules divided by our mole of zinc, which is 0.01 mole. So it would be 215 kilojoules per mole. So this is the molar enthalpy change of this entire reaction. And again, since our final temperature is larger than our initial temperature, we'll put a negative sign here, and this will tell us that this is an exothermic reaction. Alright, let's do another one. Okay, so this is a reaction for when salt dissolves in water. The salt that we're going to use is ammonium chloride. So try to pause the video and do it yourself and check if the answer is correct. Alright, so I'll take you guys through it. I hope that you get the same answer, okay? So delta H is equals to Q over mole, right? This should be your final equation. So let's find your heat energy change first. So your Q is equals to mc delta T. Your mass is 100 C, and delta T would be your final minus initial. But this time notice that your final is lower than your initial, okay? So you'll get a kilojoules here, and then you need to find the mole here, okay? So the mole should be found from the mass of ammonium chloride by dividing with molar mass. So you get yourself a mole value here. And when you divide your heat energy change by mole, you should get the kilojoule per mole, which is your molar enthalpy change. But notice here that your final temperature is less than your initial temperature. So put a plus sign in front, and this tells you that this is going to be an endothermic reaction. Alright, this one, the neutralization reaction that we're going to do is going to be slightly difficult, so please pay attention, okay? Since this is a neutralization reaction, you know that the reaction would be between an acid and an alkali. Alright, so first of all, we're going to place a polystyrene cup in a glass beaker, and then we're going to put 25 cm cube of 2 moles per dm cube of potassium hydroxide inside here. Alright, and afterwards, we will fill the burette with 50 cm cube of the hydrochloric acid, which means that this would be filled 50 cm cube with acid here. And afterwards, before we begin our reaction, we will record the initial temperature, and it was recorded to be 19.8 degrees Celsius. And afterwards, we will start to drop the acid into the mixture. Okay, we will start to drop the acid into the mixture, and at the same time, our thermometer will be inside here, and we will keep stirring it. Okay, and we will, as the volume of the acid is decreasing here or increasing here, we will record the increase in temperature as well. So we will continue adding, okay, until all the acid in here has been used. All right, so there will be no more acid in here, okay, and all of the acid and the solution will be inside here. All right, so this time it's going to be a little bit different than normal, because what you will notice here is that at a certain point the temperature starts to decrease. So why is it that is? Because when acid reacts with alkali, they will reach to a neutralization point. But after that, when you try to add on more acid, right? Since it's already neutralized, it means that all of the OH minus ions, okay? So all of the OH minus ion from potassium hydroxide has been used. So what we're doing is we're simply adding in cold acid into the solution when there is no more reaction, and that is why your temperature will start to decrease here. All right, so your final temperature that you should be writing down here is, okay, so in exam you will be given a graph like this to determine your final temperature and the volume of acid. Okay, so your final temperature is the highest maximum temperature, right? So it should be around 31.8 degrees Celsius. Okay, and the volume of HCl added, which is needed to get to the maximum temperature, if you can see here, should be 28 centimeter cube. Okay, and in the exam you should be able to explain why there is a decrease in temperature after the neutralization point. So this is the data that we recorded here. Okay, so let's try to see here. So the volume of acid is 28, so this should be 28. And the initial temperature of potassium hydroxide is 19.8, and the final temperature is recorded to be 31.8. So let's do the delta H calculation here. Alright, so let's write down the equation here first. Okay, so potassium hydroxide and will react with hydrochloric acid, and it will produce potassium chloride and water. All right, so the total volume, right? So the total volume, this time you remember that we added acid into our alkali here, so the volume of alkali was 25, and the volume of acid is 28, which should give us which should give us 53 centimeter cube, which is 53 grams. Again, I would like to remind that your delta H is equals to Q over mole. So we need to find Q and we need to find mole here. Okay, so your Q here would be MC delta T. So you already got your M here, which is 53, into your C is 4.18, into your temperature difference is 31.8 minus 19.8. If you use a calculator, you should get 2.769. okay, 2769 joules first, which would be 2.769 kilojoules. Sorry, minor calculation error here. This should be 2658. So this would be around 2.65 kilojoules. Now you need to find your mole, right? So your mole would be what? Since this is a potassium hydroxide solution, so the mole of KOH here, so it's not because this is a potassium hydroxide solution, okay? So there will be acid and potassium hydroxide, a neutralized solution, but the only concentration and the volume that we know is for KOH, which is an alkali, because we don't know the concentration for acid. Okay, so if we know it, we can find the mole from the acid side as well, but we don't, we only know from alkali. So let's do it. Okay, so since this is 25 centimeter cube, this should be 0.025 dm cube multiplied with 2 moles per dm cube, which would give you 0.05 mole. Alright, so we know 1 mole from the potassium hydroxide equation, so your delta H simply would be Q, which is 2.65, and again, try to see that your final temperature is larger than your initial, so put a negative sign, and let them know that this is an exothermic reaction. Okay, so negative 2.65 kilojoules divided by 0.05 mole. Alright, so let's try to divide it. So you would get 53, okay? Negative 53 kilojoules per mole. So that would be finding the molar enthalpy of this entire reaction. But in the case where they ask you the concentration of HCl as well, you know that 1 mole of KOH is equals to 1 mole of HCl, and 0.05 mole of KOH would be equals to 0.05 mole of HCl. And from here, you can find the concentration of HCl by dividing your mole, which is 0.05 mole, with the volume that you already know, which is 28 centimeter cube. But this time it will be 0.08, 0.028 tm cube, which should give you 1.78 mole per tm cube of concentration. Alright, so that is all for the calorimetry experiment calculation, okay? Although this might be long, try to pause the video and then try to do the calculation as I am doing along the way, and you'll be able to easily do all of this in a very short amount of time. Alright, so one thing that I would like to recap on is that for all of the calorimetry experiments, we can use a copper can or a polystyrene cup as our calorimeter. But specifically for neutralization reaction, our setup should include a burette and a pipette like we would do for titration, as it involves an alkali and an acid. Okay, I hope that this calorimetry experiment is clear to you, and I'll see you guys again soon. Bye bye.